right, so this video is going to be mostly about how we multiply an m by n matrix by a column matrix and what that kind of means and how they are related with each other. So there's a snip here from our book that if A is an m by n matrix and A is actually made up of column vectors, and then you want to multiply that by x, then really what you're doing is you're looking at something similar to a linear combination that we talked about before, right? Where you're taking x1 times the column vector of A, x2 times the column vector A2, all the way up to an. So let's look at a couple of examples here and apply this. So this is my A, and this is my column vector x. And I want to say then that this is A1, this is A2, and this is A3. So based on our definition here, this is x1, so 4 times the column vector A1 plus 3 times the column vector A2, and then 7 times the column vector A3. Then we can use multiplication like we did in our previous properties to multiply in that scalar. And then I'm going to add component-wise across the top and get -3 and 6. Oh, +3. Sorry, +3 and 6. All right, let's go ahead and look at B over here. I'll change colors so that way you can see the difference. So again, this is my A, this is my vector. And so I have A1, A2, so 4 times my column vector plus 7 times my column vector, 4 times 2, 4 times 8, -20. -21, 0, and 14. And so we end up getting -13, 32, and -6. All right, some important things that I want to make sure that I add on here and note for you is you don't really need to go through that like middle line process when we multiply a matrix A times a column vector like this. And it just is a little bit quicker to do it another way. One thing that you need to make sure that you know is this is a 2 by 3 matrix, and I'm multiplying that by a 3 by 1. So we call these, the size is the number of rows and then the number of columns. So then my resulting vector needs to be a 2 by 1, which is what we got right here. So another way that you can multiply these is similar to kind of like a cross product, if you will, is this top row needs to get multiplied component-wise with each piece here. Essentially, you're doing this all in one piece. So we do 4 times 1 plus 3 times 2 plus 7 times -1. And then we do that again. I'll change colors just so you can see this row by this column. I get 0 plus -15 plus 21. That does end up giving us our exact same solution here, and that's usually what we're going to end up doing when we're multiplying a matrix by a vector in this way. Again, it's doing this exact same steps you can see here. It's just more of like an algorithm in the way that we do it versus taking the full definition and taking that space to do so. All right, if I have these three vectors, v1, 2, and 3, and they are in Rm, write a linear combination of 3v1 minus 5v2 plus 7v3 as a matrix times a vector. Well, remember up here in our definition, it was x1, a1, where a1 was our vector, plus x2, a2, plus x3, a3. And that was equal to A as a matrix with all of those column vectors times X as a vector. So here I have 3v1 minus 5v2 plus 7v3. And so my A must be the collection of those vectors in a 3 by m, or m, I should say an m by 3, that's a better way because they're in Rm, an m by 3 matrix. And then my x here is 3, negative 5, 7 that I'm multiplying by here. And that's a 3 by 1. And so my final answer, if I were to go through and do this, would give me an m by 1 matrix, an m by 1. All right, we're going to go ahead and show how we would compute A times X here for these two matrix and then column vector pieces. Okay, so I'm going to write this A times X exactly like this. And so by that definition, I'm going to write it the long way first. That means that x1 needs to get multiplied by all of column vector 1. And x2 needs to get multiplied all by column vector 2. And x3 needs to get multiplied by all of column vector 3. I can go ahead and combine this, and I get 2x1 plus 3x2 plus 4x3 minus x1 plus 5x2 minus 3x3 and 6x1 minus 2x2 plus 8x3. Couple connections to make with you here. I'm going to change this like light purple. I could have kind of cut out this middleman here and done first row times my column vector, and notice it would have given me my first row here. This is a 3 by 3 matrix. I'm multiplying it by a 3 by 1, and so my resulting matrix needs to be a 3 by 1. And you notice I have 1, 2, 3 linear combinations, equations in this matrix, right? Notice I get my second row by multiplying second row here by my column vector, bam. Third row, column vector, here we go. Also notice that this is a system of equations. And so this is where we're coming into this now equation where we're going to be looking at AX equals a column vector B, where X and B are column vectors. So if I were to know this column vector B, I could then augment this, okay? Or if I knew the system, I can rewrite it like this, okay? And this is just another way to write an augmented matrix, but you're going to write it as an actual equation. So these things, and then you would say like augmented, and then you'd have B1, B2, B3, 3, right there. And then that would be your system. Okay, so I'm trying to make connections here in this first chapter into all of the different notations that you might see, and that they are all intertwined kind of with each other. So if we were to augment this coefficient matrix with B1, B2, B3, that's what you would get, and that's the same thing as solving that system. When we solve that system, you get your x vector, you're going to get your solution vector. Okay, and so that's just a lot of really good foundational vocab for where we are going with solving for solution vectors here in our class. Last thing are just a couple rules here. So if A is an M by N matrix and you have two solution vectors in Rn, you can add U and V and then apply A, or you can kind of like distribute matrix A to column vector U and column vector V, similar to what we would do in algebra. And if you have some constant, some scalar multiple times U, you can pull that scalar out to the very front, multiply A by U, and then apply C to all of the pieces inside that matrix.